we combine all the results, I say results all, and we bind all of those data frames that we collected. So, for example, when we did naive lasso, remember a single lasso is stored in a data frame called results naive lasso. Out of it we select just one column, the estimate, and we create a column called estimator, and we say this estimator equals to single lasso, or naive lasso, right? Then comma. This is the first data frame that we are passing to our bind rows function. The second data frame is this. It takes the results, cross-validated double selection procedure, selects estimate column, and creates a column called estimator. It's cross-validated double selection. A third data frame that we are binding rows with the previous two is results with using rigorous lasso. We select estimate again, we create estimator, we store that it is our lasso double selection, and then we also bind rows with the true OLS estimates. And remember, by default there is nothing better than the true OLS, but it's unachievable because we don't know the true functional form. So we want to compare how different approaches would be able to uncover the treatment effect without any actual knowledge of the functional forms. Then we take this will be a data frame that contains all of these different estimates for all 100 samples at different estimators. And we pipe it to the ggplot, where we say our x-axis should be estimate itself, because we want a density plot. Please differentiate different density plots by the estimator column, and please also color it differently by the estimator color. So fill is the color of the fill of the density function, and while color is a color of the line of the density function. So we want both the fill and the line to have colors that correspond to a given estimator. Then we add, as you can see, this is not a pipe operator, it's a plus operator. You add to the ggplot a layer that will plot actually the density. Alpha equal to 0.2 means how transparent it should be. If I put alpha equal to 0, it will be completely transparent, and if I put alpha equals to 1, the colors will be non-transparent at all. Since we are overplotting different estimators, densities on top of each other, we want it to be relatively transparent. Then we add another layer. It's a vertical line with an intercept of 1, which is the true treatment effect. We say the line should be dashed and the color should be red. Then we also say that the theme of the final output should be black and white, so without the usual gray pattern. And this just limits the axis, limits from -5 to 5. And then finally we also want to have the table that gives you the estimates. So here, didn't run this actual code here. As you can see, this is the figure that I supplied to you that I created on my own computer. So as you can see here, the single lasso, the post lasso inference is completely wrong. It's not even centered around, it's centered around the wrong value, which corresponds to the omitted variable bias. And now you can see all the different estimators. The true OLS has probably the slimmest standard deviations. So the true OLS is likely to be the most efficient. Cross-validated double selection estimator is slightly biased, and it looks like our lasso, rigorous lasso, is doing very well. So let's see. True OLS is the average of the true OLS is at 1.1, and the closest one is our lasso, and actually with this 100 samples, rigorous lasso is actually doing better than the true OLS. This is surprising, but this is actually just luck. When I do 1000 simulations, you can see that rigorous lasso is in fact slightly biased too. Whereas you can clearly see that cross-validated double selection is wrong. It's quite biased too.